On Christmas Day 2021, a rocket lifted off from a launch pad in South America. Nobody was on it. There were no astronauts, no flags, no speeches broadcast live from orbit. There was just a folded machine, the size of a tennis court when fully deployed, tucked inside the nose cone of an Ariane 5 rocket, and a 30-year dream that humanity was finally, after repeated delays and cost overruns and engineering nightmares, attempting to make real. It took 29 days to travel to its destination, a point in space called L2, 1.5 million kilometers from Earth, where the gravity of the Sun and Earth perfectly balance. A stable parking spot in the dark. Then it unfolded, and 44 individual mechanisms, each one a single point of failure, each one having to work perfectly in sequence, in the vacuum of space, unreachable by any human hand. The sunshield deployed, the mirror segments locked into position, the instruments cooled to their operating temperature, negative 233 degrees Celsius, 7 degrees above absolute zero. Every single one of the 344 mechanisms worked. On July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope. Scientists who had spent decades working toward this moment wept at their desks. And then the data started coming in. And almost immediately, the universe started behaving in ways it was not supposed to. To understand why Webb's findings are so disruptive, you first need to understand what makes it different from everything that came before. The Space Telescope, launched in 1990, changed astronomy forever. And it looked primarily in visible light, the same narrow band of the electromagnetic spectrum that human eyes can detect. It showed us galaxies colliding, nebulae forming stars, the deep field images that revealed thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. Hubble was astonishing. Webb makes Hubble look like a toy. Webb observes in infrared light. This is not a minor technical distinction. It is the entire ball game. Here is why. The universe is expanding. As light travels across billions of light years of expanding space, its wavelength stretches, a phenomenon called redshift. The most distant objects in the universe, the ones that formed in the first few 100 million years after the Big Bang, have had their light stretched so dramatically that it has shifted entirely out of the visible spectrum and into the infrared. Hubble literally cannot see them. They are invisible to it. Webb can see them clearly. Webb is also dramatically larger than Hubble. Its primary mirror is 6.5 meters across, 6 times the light collecting area of Hubble. Combined with its infrared sensitivity and its position far from Earth's heat signature, Webb can detect the light of a single candle flame at the distance of the moon. A candle flame on the moon from here. With that instrument, we pointed at the early universe, and what we found there is rewriting textbooks. The standard model of cosmology, the theory that describes how the universe formed and evolved, makes specific predictions about the early universe. Right after the Big Bang, matter was distributed nearly uniformly. There were tiny fluctuations, quantum ripples frozen into the universe at its birth, but broadly speaking, everything was spread out. Over hundreds of millions of years, gravity slowly pulled matter together into clouds, which collapsed into the first stars, which clustered into the first small proto-galaxies, which merged slowly over billions of years into the large galaxies we see today. This process was supposed to be slow, gradual. The early universe was supposed to be full of small, irregular, chaotic structures, the raw ingredients of what would eventually. Webb looked at the early universe and found the opposite: massive, mature, or structured galaxies, galaxies comparable in size and organization to the Milky Way, existing just 500 to 700 million years after the Big Bang. Not 5 billion years, not 3 billion years, 500 million years after the universe began. The universe is 13.8 billion years old. These galaxies are from when it was less than 4% of its current age, and they are enormous, organized, structured. Some of them have stopped forming stars entirely, a process called quenching that in our models takes billions of years to occur. These galaxies had already formed, matured, and gone quiet in a time when the universe was barely an infant. Astronomers call them the universe's impossibly early galaxy. One team of researchers nicknamed one candidate the Cosmic Seahorse. Another group, upon seeing their data, reportedly said simply, "We are not supposed to be seeing this." There are several possible explanations. Our model of how dark matter behaves may be wrong. The rate of early star formation may have been far more efficient than we thought. The way galaxies form in the very early universe may involve mechanisms we have not yet discovered. Or, and this is the uncomfortable option that keeps cosmologists awake at night, something fundamental about our model of the Big Bang, and what followed it needs to be revised. Webb has not broken the Big Bang. The Big Bang is not in question, but the story of what happened in the billion years after it may need to be rewritten from the first chapter. The galaxy problem is the one making headlines in Cosmology Journal, but there is another set of findings from Webb that may be more personally significant to every human being alive. For the first time in history, we are reading the atmospheres of planets orbiting other stars. When a planet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescope. Different molecules absorb different wavelengths of light in characteristic patterns, fingerprints. Carbon dioxide absorbs light at a specific wavelength, water vapor at another, methane at another, oxygen, ozone, sulfur dioxide. Each one leaves a unique signature in the spectrum. Previous telescopes could barely detect these signals. Webb detects them with extraordinary clarity. In 2022, Webb analyzed the atmosphere of WASP-39b, a gas giant orbiting a star 700 light-years away. It detected carbon dioxide, sulfur dioxide, water, sodium, potassium, a full chemical inventory of an alien atmosphere. It was the most detailed atmospheric analysis ever performed on a planet outside our solar system. And it was not even close to Webb's most consequential target. That target is K218b. K218b is a world 2.6 times the size of Earth, orbiting a red dwarf star 120 light-years away, sitting squarely in the habitable zone, the range of distances where liquid water could exist on a planetary surface. In 2023, Webb analyzed its atmosphere. The results were careful, caveated, and extraordinary. Webb detected carbon dioxide. It detected methane. It detected a molecule called dimethyl sulfide, DMS. On Earth, dimethyl sulfide is produced by one thing and one thing only: life. Specifically, it is produced by marine phytoplankton, the microscopic ocean organisms. It is a biological byproduct, what scientists call a biosignature, a chemical signal that, on our planet, has no known non-biological source. The researchers were explicit in their caution. The signal needs confirmation. Abiotic sources of DMS cannot yet be ruled out. More observations are required. Science demands that every alternative be exhausted before the conclusion that everyone is thinking is allowed to be stated. But the signal is there. In the atmosphere of a water world, in the habitable zone of a nearby star, there is a molecule that on Earth is made by living things. Nobody is saying it is life, but nobody can say it isn't. When Webb looks at its deepest targets, it is not looking across space. It is looking across time. Light travels at 300,000 kilometers per second, and when Webb detects a galaxy 13 billion light-years away, the light it is capturing left that galaxy 13 billion years ago. The universe was less than 1 billion years old. Whatever that galaxy is today, expanded, merged, evolved, possibly gone, we cannot know. We are seeing its infant photograph. The Webb deep field images make Hubble's deep fields look sparse. Where Hubble showed thousands of galaxies, Webb shows them in far greater number, at far greater distances, with far greater detail. Galaxies from the first few 100 million years of the universe, their light finally arriving at a telescope sensitive enough to catch it after traveling for almost the entire age of the cosmos. Some of these early galaxies are merging, colliding in slow motion over millions of years. Are their stars passing through each other like two swarms of bees merging, the gravity of billions of stars weaving two structures into one? Some contain what appear to be the earliest black holes ever observed, billions of times the mass of our sun, already existing in the infant universe, far earlier than any model predicted they could have formed. How did something so massive accumulate so much mass so quickly? We do not yet. Webb has given us the question in vivid detail. The answer is still being worked out, and the very deepest target Webb has attempted, the epoch of reionization, the period when the first stars switched on and their ultraviolet light began ionizing the neutral hydrogen fog that filled the early universe, clearing it to transparency, is now within reach. Webb is beginning to see the first light that ever shone in the universe, the moment the cosmos went from dark to lit. We are watching the universe turn its lights on for the first time. Not all of Webb's revelations are billions of light-years away. Some are practically next door. The Carina Nebula, the Tarantula Nebula, the Pillars of Creation. You have seen photographs of the Pillars of Creation. The Hubble image from 1995 is one of the most famous astronomical photographs ever taken. Towering columns of gas and dust, lit from behind by young, hot stars. A cathedral of star formation in the Eagle Nebula, 6,500 light-years away. Webb re-photographed the Pillars of Creation in 2022. The difference is not incremental. The Webb image reveals individual protostars, stars in the process of being born, still embedded in their gas clouds, or not yet hot enough to shine in visible light, but blazing in infrared, scattered across the pillars like embers. Stars that Hubble could not see because they had not yet ignited in visible wavelengths. stars being born right now, visible for the first time in human history. Webb has turned star-forming regions from abstract structures into populated neighborhoods. Every cloud of gas and dust Webb examines is revealed to be filled with protostars at various stages of formation. Young solar systems condensing, accretion disks forming, jets of material blasting out from poles of newly born stars, carving cavities in the surrounding nebula. And around some of these young stars, Webb has detected the chemical signatures of the raw ingredients for life: water ice, carbon dioxide, carbon monoxide, like complex organic molecules including ethanol and acetic acid, molecules that on Earth are associated with chemistry that precedes biology. These molecules exist in the cold gas clouds that collapse to form solar systems. They are incorporated into asteroids and comets during planetary formation. They are delivered to young planets by impacts in the early solar system. The way many scientists believe the chemical precursors of life were delivered to early Earth. Webb is watching this process happen in real time, in dozens of star-forming regions simultaneously. It is documenting the chemistry of becoming, the universe preparing the ingredients, assembling the kit, setting the stage. For what exactly remains the most important open question in science. There is a number at the heart of cosmology, a number so fundamental that if it is wrong, our entire model of the universe needs to be rebuilt. It is called the Hubble constant. It describes the rate at which the universe is expanding, how fast galaxies are moving away from each other per unit of distance. It is the heartbeat of the cosmos. Get it right, and you can calculate the age of the universe, its ultimate fate, the nature of dark energy. Get it wrong, and the entire model collapses. For years, astronomers have measured the Hubble constant using two independent methods. And the two methods give different answers, not slightly different. Significantly, stubbornly, persistently different. So different that the statistical probability of it being a coincidence or measurement error is less than 1 in a million. This discrepancy is called the Hubble tension, and it is the biggest unsolved problem in modern cosmology. One of Webb's primary missions was to resolve it, to measure the Hubble constant with such precision that the discrepancy would either be explained by old measurement errors or confirmed as a genuine crack in our understanding of the universe. Webb's measurements confirm the discrepancy is real. The tension is not a measurement error. It is not an artifact of imprecise instruments. Webb has ruled that out with a level of precision Hubble could never achieve. The universe is expanding at two different rates depending on how you measure it, and that should be impossible. A universe cannot have two expansion rates. It is one universe. There is one rate, which means one of three things. Our understanding of dark energy, the mysterious force accelerating the expansion of the universe, is wrong. Our understanding of dark matter, the invisible scaffold on which all visible structure rests, is wrong. Or there is new physics, something we have not yet discovered, a piece of the puzzle that is not in any textbook, not in any model, not in any equation, currently written on any whiteboard in any physics department on Earth. Webb did not solve the Hubble tension. Webb proved it is real, and in science, confirming that a problem is real, that it cannot be explained away, is the necessary first step toward solving it. We are at the beginning of something. We do not yet know what. Every instrument humanity has ever built to look at the sky has done the same thing. It has pushed the boundary of what we thought we knew, and replaced certainty with a larger, stranger set of questions. Galileo pointed his telescope at Jupiter and found moons, objects orbiting something that was not Earth, shattering the idea that everything in the sky revolved around us. Hubble's telescope revealed that the fuzzy patches astronomers called nebulae were not clouds inside our galaxy. They were entire galaxies, billions of light years away. The universe was not the Milky Way. The Milky Way was one galaxy among hundreds of billions. The Hubble Space Telescope revealed that the expansion of the universe is accelerating, driven by a mysterious dark energy that makes up 68% of everything that exists and that we understand almost nothing about. James Webb is doing it again. Every generation of instrument that has expanded our view has found, without exception, that the universe is larger, older, stranger, more structured, more complex, and more full of mystery than the generation before it imagined. Webb has found galaxies that formed too early, black holes that grew too fast, a possible biosignature on a water world 120 light-years away, a confirmed tension in the expansion rate of the cosmos that points to missing physics, and it has been operational for less than 3 years. It has a designed lifetime of 20 years. Thanks to the precision of its launch trajectory, Webb may actually operate for far longer than that. The fuel it would have used correcting launch errors was not needed. The reserves are intact. Webb may be sending data back to Earth for 30 years, 40 years, longer. What it finds in that time, nobody knows. But the history of telescopes is unambiguous. Every time we built one powerful enough to see further than before, reality turned out to be different from what we expected. Not slightly different, fundamentally different. Every single time. There is a photograph Webb took in 2022. It is called the Webb Deep Field. It shows a small patch of sky, smaller than a grain of sand held at arm's length. In that patch of sky, there are thousands of galaxies. Some of them are nearby, cosmically speaking, a few 100 million light-years away. Some are billions of light-years away. The most distant visible in that image are from a time when the universe was less than 1 billion years old, their light having traveled for over 13 billion years before landing on Webb's mirror. Every point of light in that image is not a star. It is an entire galaxy. Hundreds of billions of stars. Hundreds of billions of potential solar systems, each one a place where, for all we know, something is looking back. Multiply that patch of sky by the entire sky above your head, and the number of galaxies in the observable universe is estimated at 2 trillion. 2 trillion galaxies, each containing hundreds of billions of stars. Most of those stars with planets. Many of those planets in habitable zones. Some of those planets with atmospheres. Some of those atmospheres containing molecules that on Earth are produced by life. Webb is not answering the question of whether we are alone. It is making the question undeniable. It is forcing the universe to show us its full scale, its full complexity, its full chemical richness, and daring us to still believe that in all of that, in 2 trillion galaxies and hundreds of billions of years of cosmic history, The only place anything ever happened was here. The early results suggest we built our models on incomplete information. That the universe formed faster, structured itself earlier, and operates on rules we have not fully written down yet. The most honest thing any astronomer will tell you right now is this: we thought we knew the broad outline. We thought the details were left to fill in. Webb is showing us that what we thought were details are load-bearing walls, and some of them are not where we expected. The universe is not behaving. And that is the best possible news, because every time the universe has refused to behave, every time the data has come back wrong, every time an instrument has shown us something that shouldn't be there, it has meant that reality is larger than our model of it. It has meant there is more to find. Webb just started looking.